Hi, this is David.
Hi, this is Travis.
And this is Tim, and this is going to be our presentation on thermodynamics.
Alright, David again. I'll be going over the basic information you guys will need to know. There are three main laws of thermodynamics. The first law states that energy is conserved and its form can be converted. The second law states that energies can flow and equilibrate. And the third law is also known as driving force and states that equilibration is uniquely defined within every substance. Alright, our first topic is heat, work, and internal energy. Temperature is the quantity of kinetic energy in a molecule. When you change your temperature, you also change your energy. And the faster the movement of the molecules means you have more internal energy. Energy transfers between molecules in the form of heat. Heat is transferred when molecules collide. When molecules collide, this alters the temperature of both objects as they reach thermal equilibrium. And thermal equilibrium occurs when the temperature of two touching objects becomes equal. Thermal equilibrium will reach an average temperature between that of the initial two temperatures. So if you see the diagram, you have an object that has 0 degrees Celsius, and you have an object that has 100 degrees Celsius. Now, assuming both objects are the same mass, you'll have a resulting temperature of 50 degrees Celsius when they reach thermal equilibrium. The book briefly mentioned thermometers, so I'll just go over how they work. As a thermometer gives or takes heat, the mercury inside increases or decreases in volume. Now this, of course, doesn't take into account modern-day thermometers that are electronic because they don't have any mercury inside them. Specific heat is the energy required to change the temperature of an object. Specific heat depends on the mass, type of material, and temperature change. And this can be seen in the equation Q equals mCp delta T. While your Q is the amount of energy in the system, your M is your mass, your Cp is your specific heat value, which is given, and delta T is your change in temperature. Latent heat is the energy required to change the phase of a substance. Latent heat depends on the molecular composition of the substance and the mass. And this can be shown by the equation Q equals mL, where Q is again the mass the energy in the system, M is the mass, and L is latent heat. And like specific heat, latent heat is a value given. Now there are three main phases of matter. You have your solid and your liquids and your gases. Solids are molecules that pack closely together and they have very low kinetic energy. Liquids have no compact shape and they form to their environment, and they have medium kinetic energy when compared to solids and gases. Gases are spaced very far apart and they have very high kinetic energy because molecules are moving around very fast. If you look at this diagram, solids have a definite shape, a definite volume, and are the most dense phase. Liquids take on the shape of the container and they have a definite volume. Gases take on the shape of and volume of the container, and they'll spread out to do so, and they are the least dense. Matter can change phase when temperature or pressure is increased or decreases. There are two main types of phase changes that we talked about in physics. Now there's a third one called sublimation, but we won't go over that. There is fusion, which is when matter changes from solid to liquid or from liquid to solid. And you can imagine this by freezing or melting. Then you have your vaporization, which is when matter changes from liquid to gas or from gas to liquid. And you can see this when matter condensates or evaporates. Let's reinforce your understanding of thermodynamics with some example problems. Tim, take it away.
Alright, this is Tim here. Now, the basic way to understand some of these ideas would be through conceptual questions of everyday activities that you would experience. Like, for instance, if you have an aerosol can filled with paint, and at first it starts off at room temperature, and then you spray it for about 30 seconds. Initially, if you recall, it was at room temperature, yet after being sprayed for about the 30 seconds, the can feels cool to the touch. Now, what process could possibly cause this whole can to become cold after being sprayed for an amount of time? The answer is that energy is within the can, held by the gas that is constantly creating pressure within the can. As you press the nozzle on the top and release the energy from the can, the energy is being transferred from the pressure and releasing the paint from the can out. Releasing the energy causes the heat to leave the can, but cool the can down. Another good question would be, well, because energy is transferred through heat, can energy only be transferred using the laws of thermodynamics? And the answer to that is, well, there are multiple forms of energy transfer, such as things like electrical energy that can easily be transferred across wires, or other things through different materials. And just because the materials are transferring energy, it doesn't necessarily mean that the transfer is thermodynamic.
Alright, if you guys don't remember me, I'm Travis Tran, and we're going to go over some math problems. Here's problem number 1. If there are 500 joules of energy and the mass of a metal is 100 kilograms, what is the specific heat of the metal when the temperature went from 15 degrees Celsius to 34 degrees Celsius? The answer? Well, first off, energy equals 500 joules, mass equals 100 kilograms, and we're trying to solve for a specific heat, and our delta T, or change of temperature, equals 34 minus 15, which equals to 19 degrees of Celsius. And then the equation we'll be using is Q equals mCp of delta T. So if we plug in all the numbers, we get 500 equals 100 times specific heat times 19. Therefore, we simplify, we get 500 equals 1900 times specific heat, and our final answer should be around 0.263 joules per kilogram. Alright, our second math problem. If the latent heat of an unknown object is 25 joules per kilogram and the mass of it is 20 kilograms, what is the energy required to change the phase of the unknown object? Well, answer, latent heat equals 25 joules per kilogram, mass equals 20 grams, and we're trying to find energy. Therefore, we use the formula Q equals M times L. Therefore, if we plug in the numbers again, we get Q equals 20 times 25, so therefore our final answer should be 500 joules. Now, our last problem. Using the information from the previous slide, the latent heat of the unknown object to become liquid is 500 joules per kilogram. What is the final temperature of the liquid if the initial temperature of the liquid is 20 degrees Celsius? Assume that the specific heat of the liquid is 100 joules per kilogram. Well, in the answer from our previous slide, or the second question, Q equals 500 joules. We're trying to find mass, and our latent heat equals 50 joules per kilogram. Delta T, which equals to final temperature minus initial temperature, which would be 20, which our initial temperature would be 20 degrees Celsius, and then our two formulas we'll be using are Q equals ML, Q equals mCp delta T. So, therefore, we plug in the numbers for the Q equals ML, we get 500 equals mass times 50. Therefore, our mass will be 10 kilograms. Now we plug in all those numbers into the second formula, which will be the Q equals mCp delta T, and we should get 500 equals 10 times 100 times, in parentheses, final temperature minus 20 degrees Celsius. Therefore, we simplify, and we get 0.5 equals final temperature minus 20, and then our final answer should be around 20.5 degrees Celsius.
Now to start the fun portion of our project in thermodynamics, we're burning gummy bears and gummy worms. So, as you can see, what's going on is that the water inside the gummy bears and gummy worms is boiling, and it's turning from a solid to a liquid, and then there's water vapor coming out, which is a gas.
Keep going. Cash really likes
More lighter fluid.
Mr. Uhlar would appreciate all of this.
There you go. There you go.
Burn. This is all on recording, by the way.
Yeah, I know. Trust me, I know.